Welcome. So you've probably heard people talk about how fast an algorithm is, right? But how do they actually measure that? Well, today we're going to pull back the curtain on asymptotic notations. This is the real language computer scientists use to talk about performance. Let's get into it.
Here's the game plan. First, we'll talk about why we even need this stuff. Then we're going to build a really simple mental map, the ceiling, the floor, and the room that's going to make everything else click. After that, we'll dive into the details of big O, omega, and theta, and we'll wrap up by clearing up a mistake I see students make all the time.
So why can't we just, run an algorithm and time it with a stopwatch? The thing is, an algorithm's runtime isn't a simple number. It's often a really messy mathematical function. We need a cleaner, more universal way to talk about how it performs as the amount of data grows, without getting totally lost in the weeds.
And that really is the million-dollar question, isn't it? How do we boil down all that complexity into something simple that we can actually use to compare one algorithm to another? Well, this is the exact problem that asymptotic notations were invented to solve.
Okay, to make this all feel real, let's use an example that we'll stick with for this whole explainer. Imagine we've analyzed an algorithm and found its time complexity is exactly f of n equals 2n plus 3. I mean, that's precise, sure, but it's a little clunky. We're looking for a simpler, higher-level way to talk about how this function grows.
All right, before we jump into any of the formal, kind of scary-looking math, let's build ourselves a powerful mental model. This simple analogy is going to be our guide for understanding all three notations. I promise, it helps a ton.
I want you to picture our function, that 2n plus 3, as something that lives inside a room. Now there are three ways we can describe where it is. We can talk about the ceiling high above it, we can talk about the floor down below it, or we could just describe the entire room that it's stuck inside. Each one of these ideas maps perfectly to the notations we're about to learn.
So first up, let's talk about the ceiling. In our world, this is big O notation. It sets an upper bound, a limit. What it's really saying is, hey, I guarantee you, my algorithm will never perform worse than this. It will not grow faster than this ceiling, no matter how big the input gets.
All right, so if the ceiling is big O, then the floor is big omega. It's pretty much the exact opposite. It sets a lower bound. It's a guarantee that our algorithm will never be better than this floor. It's always going to take at least this much work to get the job done.
And that brings us to the room itself. This is theta notation, and it's the most precise description of them all. Theta tells us that our function is literally sandwiched between a floor and a ceiling that are growing at the same rate. It's not just a limit anymore. It's a tight, accurate description of the function's actual growth.
Okay, you ready? Let's put some real math behind that analogy. We're going to start with big O, our ceiling, and see how we can formally define what an upper bound actually is.
Okay, don't let the symbols intimidate you. This is literally just our ceiling analogy written in math speak. It says our function, f of n, is big O of g of n if we can find some other function, g of n, that will always be bigger than ours. That c and n0 are just little tools that give us some wiggle room to make it work for large input.
So let's actually do it for our f of n equals 2n plus 3. The goal is to find a g of n that works as a ceiling. A simple guess is just g of n equals n. Now, can we find a constant c to meet the inequality true? Yeah, for sure. If we pick c equals 5, the statement 2n plus 3 is less than or equal to 5n is true for any n bigger than 1. And boom, just like that, we've proved our function is O of n.
Now pay attention, because this is a really important point, especially for exams. A function can have lots of ceilings. For our function 2n plus 3, saying it's O of n squared is technically correct, because n squared grows way faster. O of 2n is also true. But saying it's O of log n is totally false. Log n grows slower. That's a floor, not a ceiling.
And that leads to this crucial point. Just because a statement is true doesn't mean it's useful. When we talk about big O, what we really want is the tightest, closest ceiling we can find. For 2n plus 3, that is absolutely O of n.
All right, we've got the ceiling figured out. Let's move on. Now it's time to go down and define the floor using big omega.
Now look closely at this definition. Does it look familiar? It should. It is almost identical to the big O definition, but with one single critical change. The inequality sign is flipped. Now we're looking for a g of n that will always be smaller than our function. We're finding a floor.
Let's go back to our trusty example, 2n plus 3. We need to find a floor for it. And again, let's just test g of n equals n. Can we find a constant?
This one's even easier. If we just pick c equals 1, the statement 2n plus 3 is greater than or equal to 1n is obviously true for all positive numbers. So we can confidently say our function is also omega of n.
Okay, this is where it all comes together. We have our ceiling, which is big O. We have our floor, which is omega. Now it's time to put them together and define the whole room with theta notation.
And this definition perfectly illustrates that sandwich idea we talked about. For a function f of n to be theta of g of n, it has to be trapped. It has to be bigger than one version of g of n, that's the floor, and smaller than another version of g of n, that's the ceiling, at the exact same time.
And look, this table lays our proof out perfectly. We already did the work. We found a floor, 1n, we found a ceiling, 5n, and our function, 2n plus 3, is sitting right there in the middle, perfectly sandwiched between two different versions of n. That's everything we need.
So here's the big final takeaway. Because our function is both big O of n and big omega of n, we get to make the most precise statement of all. It is theta of n. This tells us the function's exact order of growth, and that's why it's the gold standard. It's the most useful notation whenever you can prove it.
Before we wrap this up, I want to tackle one of the single biggest points of confusion for students who are new to this. You absolutely have to understand the difference between these notations and something called algorithm cases.
Please burn this into your brain for your exams. Asymptotic notations, big O, omega, theta, are just a mathematical language to describe how fast functions grow, period. Algorithm cases, like best case, worst case, average case, are about the type of input you're giving the algorithm. They are two completely different ideas. You could, for example, describe the worst-case runtime of an algorithm using theta notation. Any notation can describe any case. Don't mix them up.
So, we've built a really solid foundation today, right? We went from a simple analogy of a room all the way to formal proofs. You now have the language to precisely describe an algorithm's behavior. So the question I want to leave you with is this. How would you start to analyze the efficiency of the search engines, the sorting functions, and all the other algorithms that power the technology you use every single day? You actually have the tools to start thinking about that now.